introduced force directed scheduling, and the main idea was that you would like to uniformly distribute the operations across the clock cycles wherever you have the possibility of doing so. Of course, at times there are dependencies because of which we do not really have a choice, we have to respect the dependencies. But within that, when we do have a choice, the idea of time constraint scheduling is that if we try to uniformly distribute all the operations, then we would end up with a minimal resource count. Okay. So, let us look at the details of this force directed scheduling algorithm. This too is a strategy with a number of variations. What we will introduce is the basic idea. You can see there are opportunities for improving in a number of ways. So, get back to the ASAP and the ALAP as a way to influence some of the decisions here. The ideas are similar to what we had seen in list scheduling, but they are executed in a different way. So, let us go ahead and perform the ASAP, which gives us a minimum delay schedule assuming infinite number of resources. We also perform an ALAP, which gives us a schedule taking into account the deadline that was specified. This is time constraint scheduling, so a deadline has been specified. So, in our example here, the deadline was 4, but it need not be 4, of course, but we come up with an appropriate ALAP schedule whatever the deadline is. Having come up with these two, let us identify the scheduling ranges as we had done earlier, which is for these operations 1 and 2 and 6 and 10 and 11. You do not really have any flexibility. So, you have to schedule them into their respective clock cycles. Remember that if the deadline was different from 4, then all the operations would have some scheduling range. Okay. So, that is what we have for nodes like 3, that one we have some flexibility because that could go into the first cycle or into the second cycle. So, these bars here represent the range of cycles to which each of those individual operations could be scheduled. So, let us take a subset of the operations. Here we have multiplication and addition and subtraction, comparison. So, several kinds of operations. So, let us just take the multiplication. This has to be separately done for all the different resource types. So, these are the multiply operations, right, all of these 4 and these are our multiply operations, and look at their scheduling ranges. We identify these. Some of these like 1, 2 and 6 we do not really have a choice, but the others 3, 4 and 7 we do have a choice. So, let us identify the schedules for these. That is essentially what the scheduling strategy would be. Now, just for the multiply operations, I have to repeat that process for the other operations also. Problem of course, is that I do not have the flexibility to exhaustively consider all the operations being scheduled to all the cycles to which they could be scheduled, because that could be a large number. So, this strategy first determines a scheduling probability for every multiply operations. For these nodes like 1, 2 and 6 we do not have a range. So, the respective probabilities are 1. Okay. The others like 3, it could be here or here. So, let us say that that probability of going there is half and probability of going there is also half. The same thing I do for number 4, it could be into any of those 3. So, I have with a 1/3 probability it could go into this or this or this. So, that is the construction of a probability. This is done just so that it helps us simplify the the algorithm, so that again we do not revisit decisions that are made, but hopefully the one time decision that we are making is a good one for every operation. Okay. If you look at the distribution of the probabilities of all of these operations, that picture actually gives us some idea about the kind of resources that may be needed. In what way? So, let us say I add up the respective probabilities of all of those operations that have a probability of being non-zero probability of being scheduled into the first cycle, and I get a number like 2.83. If I add up all of these, I get 2.33 and so on. If I add up these, I get this. So, what does this tell us? That distribution graph tells us something about the resource cost. What does it tell us? So, 2.83 versus 0.83 means that you are likely to need more resources in the first cycle than in the third cycle. Okay. In what way? So, that max expected operator cost, that is the number that we are computing. For each of the cycles there is an expected operator cost. The maximum out of them tells us what? That number is capturing some information that is relevant to us. What information is it?
We do not need more than this resource.
It tells us how many resources are needed. There are, this is not an integer number, so it is not exact. These are probabilities, so they may or may not be respected. The specific decision may or may not be respected, but out of these three numbers, if I look at the max, that tells us how many resources I might need. That could be used in an algorithm that makes up the final decision, but this expected operator cost, just that distribution graph carries some meaning which could be exploited in a specific algorithm. How do we exploit it? It is not so hard to weave an algorithm around that idea. Yeah.
Last picture. Does algorithm also analyze something like, we have this fourth bar which is one third of probability across 3 cycles.
Yes.
Now, rather than considering it in first 2 cycles, if I distribute to the third cycle where the number is very low, so if I do an average distribution, then probably the maximum number of resources which I will need may reduce.
Yeah, remember the intuition is that we try to uniformly spread out the resource usage across the clock cycle. That of course would be the objective. So, somehow our objective in an algorithm, we did not get to an algorithm, this is only giving us a picture of what is going on without taking any decisions. But the process of making those decisions can take this into account, that we want to minimize the maximum expected operator cost.
It is a formalism of improving beyond ASAP if you want to reduce the resource.
Yeah, ASAP is bad from a resource, well, it could be bad from a resource point of view, right, because first of all it is assuming there are infinite resources. The resource, no constraint was of course taken into account in coming up with ASAP. So, if you have a large number of operations, for example, that do not have incoming edges, then all of them will float up to the first cycle, and it almost by definition for practical graphs, it leads to a very uneven distribution of resources across the cycles. There is nothing central to the algorithm itself, but commonly the kind of graphs that we have in practice may be such that a lot of these independent operations that are not dependent on any other operation occur early on, and therefore, they may all get pushed up to the earlier cycles. Okay. Having identified that distribution graph, you can come up with a simple strategy. You take each of these operators that have some scheduling flexibility, where the scheduling range is more than one cycle, and evaluate the impact of assigning it to the first cycle, to the second cycle, to the third cycle and so on. So, we try to schedule it here, see what happens. We try to schedule it here and see what happens. Hopefully, not too many choices are there, but at the end of the process we finalize the schedule for that particular operator 3. This is all that we are doing. Essentially what we are doing is, we had this bar here, we convert that probability into a 1 here, okay, which means that I have taken temporarily the decision to schedule that operator 3 into clock cycle 1. Then I look at the distribution graph and see what has happened to it. What I am interested in is this number, which is the maximum cost out of all the expected costs. So, that maximum cost is 3.33. I can also in an iterative manner schedule that one to this other clock cycle and correspondingly determine what the cost would be. This is still an expected cost because the decisions for these nodes have not been taken, for 4 and 7 have not been taken yet. So, there is the question of in what order you will actually look at these operators, because the decisions might actually be influenced by that. But this is an example. I go ahead and continue this process, temporarily schedule that operator into the second cycle and see what is the impact. If I had this kind of a distribution where I had taken this decision and let us say I am trying to evaluate the impact of node 7 being scheduled into one cycle or this or the other cycle, I can correspondingly keep track of these distributions, and for each candidate that we are looking at, we can look at the maximum expected operator cost. So, temporarily for an individual operator, we go through the different cycles, try to assign it to each cycle in its scheduling range, compute the expected operator costs, the max expected operator cost, and finalize the decision for that operator. So, then that probability becomes 1 for whichever clock cycle we assigned it to, and then I just continue with the rest of the operations. Yeah.
So, if I understand correctly, what currently we are doing is we are trying all permutation and combinations of, if I take this bar to one of the cycles where it is possible to schedule that, right? So, these permutation and combinations could be very huge.
Oh, yeah, we are not trying out, at least this algorithm is not doing so. Let us say, so these are my cycles and I have some such distribution, right, each is one cycle. So, the real number of choices I have is 3 here times 2 here times 4 here times 3. That is how many choices I have. One of them is the optimal, but the strategy that I just said is not evaluating all of them. In some order of the operators, it's picking that. I did not say what the order would be. Let us pick up this one first. It is evaluating the impact of scheduling this operator into one of the 3 cycles that it could go into. Once I made the decision that this is going here, I fix it and then I proceed to the next one, maybe this. So, the number of combinations I am evaluating is much smaller.
You are just looking at one process at a time.
Right,
The
it is.
is not the product, it is the sum of all.
It is the sum,
Yeah,
right.
but
It's the sum.
that will not give the most optimal.
Yeah, in the process you might miss out the best solution indeed.
So, how we arrive at this ranges?
Ranges are arrived at by doing the ASAP and ELAP.
Okay.
ASAP tells you the earliest
Mobility.
cycle, ELAP tells you the latest cycle, and that is how you come up with the range. The heart of the strategy is this. As you can see, there are opportunities for improving the quality of this result by doing various things. Among other things, what can we think of as variations of this basic strategy? I could still retain this as the heart of the evaluation strategy, but an important element that was missed out here is we did not take the order into consideration. How could we take that into in some simple way?
order as in the.
Yeah, why should I start with this? Maybe I could have started with this.
Pick the longest bar
Pick the smallest.
and
Pick the smallest one.
Smallest.
First and then schedule it first.
smallest one is already.
Yeah, between the longest and the shortest, maybe we have the answer somewhere. But actually, neither of them might be an optimal strategy. This is we are only trying to hopefully improve upon the basic strategy there, which was a random choice of the operations. There could be some argument for picking up the node that has the shortest range.
So
what is
if,
that argument?
If I start with the shortest, then by the time I'll reach longest, I'll have more opportunities to get it adjusted.
This argument we actually used in the list scheduling also. The priority was determined by the mobility of the operation. More mobility means lower priority. Same thing could also be used here, which is those could be the if the mobility is smaller, which means that the range is smaller, then they could be the higher priority operators. Still not guaranteed, but it could be one way of sorting the order in which we evaluate the nodes. Anyway, it brings down the complexity significantly, does compromise on the quality of the result, but as opposed to the product of all these ranges, which could be an exponentially large in the number of nodes that have non-zero scheduling ranges.
So why are we starting with ASAP graph first and not ALAP? I mean, in that sense.
We are constructing this range.
Right.
This range is determined by two numbers, the ASAP number and the ALAP number. So there is no relation between the two schedules. So you do it independently.
There is an assumption that we are starting from the ASAP one first. If
I have to determine this number, I have to determine this number, right?
that is done.
Right.
If I start with shortest, that means I am starting with the ASAP and then going to the most relaxed. So I am starting with the most resource required thought process to a relaxed resource required thought process, which is okay, but this is one way of looking at
This kind of a strategy is okay. Sometimes actually you can prove that it is optimal for certain classes of problems. Here it is not necessarily optimal, but we are just saying that the nodes that have more flexibility, those it is possible that you have good solutions even though you have made some other intermediate decision. So, let us say this one has a range of 4, maybe by the time you reach there, these clock cycles are already full of other operations. Okay, because I have already taken decisions for this, this and this. That clock cycle maybe I have already inserted too many operations, but because the range was larger, I can take this, I can take this, I can take. So, I could possibly schedule that operation into any one of the other cycles which are less busy. If it was the other way around, that is I started with this one, initially when I start off, perhaps there is nothing that is stopping me from assigning this to this cycle itself. Okay. Now, in retrospect, later on it might seem that when it comes to this guy later on, I really do not have a choice and I have to schedule that into one of the cycles that is already busy and I did not anticipate that this other operation.
I have the EOC in place, right. So, if I have EOC in place, I need to move the largest bar, I need to pick things from the largest bar to the smallest bar.
So
I can choose that as my strategy and I can look at the longest to
I
choose
think
that.
The EOC is there, remember it is EOC is an expectation, it is anticipating what you will do in the future, but these decisions that you are taking immediately are definite decisions. As a result of this, you know it is going to be 1, the others are still there. So, there is a backup against giving very bad solutions, but
And I can choose that 3.33, I know that this bar is longest, I will pick that one from that and move it to 1.33. So, I will start with the longest.
As what you are saying is another variation of the algorithm. That so a number of variations are of course possible. What we are just pointing out is a basic representation that will help us evaluate different choices. It is not as simple as just the ordering. There are a number of other things. So yes, intuitively the idea is we try to shuffle these in a way that we are able to compact.
Local versus global picture. The shortest path method will look at the local picture more. I was thinking more about the global picture by looking all EOCs in parallel.
So basically,
You could in fact look at the distribution graph, and your algorithm could be based on analyzing that distribution graph, and from there proceed to the nodes. That is the other way around.
Optimization tools that we work with in VLSI goes through a global pass first, then they attack the local pass. This is a usual process.
We will look at examples. See, the point of showing this is to illustrate the representation that captures some of the trade-offs that are involved. And of course, we discuss here what are the simplest algorithms. There are a number of different ways. Even the whole of the high level synthesis formalism that we are looking at is a very local optimization. Resource constraint scheduling is an example of a rather local way of formulating the problem. Your real problem, remember, is that you have even in the context of resource constraint scheduling, you have an area constraint. If at all, there is a area constraint may be derived from the cost of the chip or something like that, right. But who is telling you that you should have 2 multipliers and 4 adders? Why should somebody give that information? That should be something you can argue. It should come out as part of the exploration of the tool itself. Keeping the, let us say, the area equals 10, if you knew that plus was plus had 2, so whatever those units are, and the multiplier had 3 square microns. So, some such areas were there. This area of 10 could translate into multiple resource distributions, all of which add up to less than or equal to 10, right. I can have 3 adders and 1 multiplier. That's a total area that is less than 10. It could also be 2 multipliers and 2 adders, right. This is 10. More likely, that's the constraint that you are working with. That in turn translates to this. As you know, if you set the resource constraints as these, then you get one set of schedules. If you set the resource constraint to this, then you get a different schedule. The way we formulated the resource constraint problem, we are assuming that the number of resources of each type is given. But in reality, that might not be. You can see that this is simplifying the practical problem. Practical problem is more likely to be that there is an area, and within that area you want to get the best possible circuit in terms of delay. But while that is understood, it is not hard to see a connection between reusing the same strategy, resource constraint strategies that we looked at in this formalism, where the constraint is not on the number of resources of each type, but on the total count. How would you do it?
Similar kind of EOC.
I can have some strategy for generating different combinations that are promising, let us say. How I do it is a different matter, but as part of that generation process, these 2 specific resource count oriented constraints could be generated, and then I could use my list scheduling the way I had formulated it. So, yes, there is a bigger picture that can often be constructed using multiple iterations of the core algorithms that we are looking at. And while through this course we may not be able to explore the entire space that is there, the focus is indeed to look at the core algorithms. That is why we are dealing with what seem to be little local versions of the optimization problems. With that, the strategy is actually very simple. Find the assignment of the operator to the control step that minimizes the maximum EOC. You fix the schedule of that selected node, fix the schedule translates to making its probability 1 in the distribution graph for subsequent iterations which see that selected schedule as showing up and influencing the probabilities of the graph that they see. It is a constructive algorithm, you do not revisit the scheduling decisions once they are taken. However, the result that you come up with could still be submitted for further improvement in some iterative improvement kind of strategy, where you just take a given schedule and maybe do some local or global variations in the schedules of the individual nodes to see whether there is an improvement. That is always possible, right. The schedule that you are given is the starting point, that of course respects the deadline, respects the time constraint, and within that as long as that deadline is respected, you can try to move nodes to different cycles within its scheduling range in the hope that you might discover some solution that was missed out earlier. Okay. So, that is the two basic scheduling strategies. One was a resource constrained scheduling and the other was a time constrained scheduling. This itself is a much more complex topic, but the idea here was that we get some basic idea about how to go about formulating the respective scheduling problems, and how to come up with some simple heuristics that are practical in nature. These are all of a practical nature, these algorithms that we have studied with, both the list scheduling and force directed scheduling and so on. They are not very complex. We did not explicitly analyze the complexity, but you can see that at least the basic strategy is not complicated at all. You can try to make it more sophisticated, but there is usually a trade off between execution time and the quality of the synthesis algorithm. The binding is a general problem that occurs in the synthesis, where many different problems actually fit into the overall context of binding. Resources are there, you have already taken the decision through scheduling or something that these resources are going to be used. Operations are there, operations have already been mapped into specific clock cycles, right. At the end of the scheduling, we have taken the decision that 2 adders are there in clock cycle 2 and 1 adder is there in clock cycle 3. That is enough for the scheduler to guarantee that it is possible. If you had 2 resources, such a schedule is feasible. But the information that is not yet there is which resource should perform which computation. Okay. So, you have the choice of sharing the resource between these two, one resource between these two operations and the other resource doing that, or it could also be that you do that kind of sharing. So, the binding problem refers to the assignment of individual operators that have already been scheduled. In the case of function unit binding, it refers to the problem of assigning individual operators that have already been scheduled to the specific function unit. That too is an interesting problem, but this is not the only kind of binding that is involved here. We could also talk about binding variables to registers. That is also a binding problem. I have some registers, I have some variables, those variables translate to what in the data flow graph? Those variables are captured in edges essentially. The edges have a label and that label is just that variable. Right. If that edge is crossing a clock cycle boundary, then we said that a register is inferred. But there is this question of which register should contain which variable. There are also other interesting problems that come up when you impose some restrictions about the target architecture. Binding data transfers to buses is one of them. It did not show up as of now in the formalism we have introduced so far for high level synthesis, but there is one assumption we have made about the connectivity between function units and registers, which is what? What is the assumption we have made? Data can flow from any function unit to any register. All of them could be active simultaneously. All the data transfers could be active simultaneously. So, if you have m function units and n registers, you could have an architecture as a consequence of all the synthesis that we are doing, in which all the m are actually connected to all the n. You could have, right, paths could be established from all the registers into function units and all the function units into the registers. So, it is a fully connected interconnection structure, which for various reasons could be inefficient. It may become inefficient later on, even though at this logical level we are not able to see it. It has not been incorporated in our decisions in any way yet. It could be that it interferes with the good routing later on, because there are too many wires. Therefore, you could think of imposing some constraints perhaps on that target architecture. Do not allow the tool to just assume anything can be connected to anything else, but it could be that you specify a template for an architecture that looks like this. There are some buses around which your connectivity should take place, okay. And the function units that you have should all be connected to those buses, and your registers should also be connected. Just an example of a template. So, how they are connected is up to you, but this could be connected to this, it could be connected to this, each of them could be connected in this way. You decide what those connections are as a result of the synthesis. Similarly, the registers could be connected to possibly to all of these, right. So, but that is the extent of the flexibility you have in the connections. Okay, let me add one more function unit. Maybe it is okay. What this permits is that I am of course able to connect any function unit to any other function unit. That is okay, because I can just establish all of these connections and it is fine. Right, all of them could be connected. So, paths are certainly there to any function unit, to any register, but what constraints does it impose? The number of buses is limited, therefore, the data transfers that are simultaneous data transfers that are permitted in this structure are limited. This is similar to the memory port related argument. You could access any data element, but simultaneously there is a limit to how many data elements you can access. So, here if I say that R1, R2, R3, if I say that this is F1, F2 and F3, that F1 is going to transfer its data to R1, F2 is going to transfer its data to R3 in the same cycle, then I can't use that connection. I have to use some other connection like this. And if I in that same cycle, if F3 were to send its data, let us say to R2, then I would be let us say I would be using this connection. Now, so this was okay if there are 3 simultaneous transfers, all of them going to each. If I had a fourth one though, let me extend this. So, this is another FU and I had a fourth register. So, what I am limiting through this structure is the number of simultaneous data transfers. I have to wait. I may have this F4 being ready to send its data to R4, but I do not have a mechanism for, even though the connected structure is there. So, this is also connected to all of these and this too is connected to all of these, but in that particular clock cycle I do not have the resource. So, you can think of these buses as also resources that need to be scheduled into particular clock cycles.
Basically, for each mathematical operator or operator we are looking in the graph so far examples, we should also think of fetch and post as operations, and then we can put buses as number of.
Right. So, you can see that such a structure has its advantages and has its disadvantages. Advantage is that it controls the layout and the routing in a, the placement and the routing in a more reasonable way. So, that would lead to a better architecture later on in the physical design step. Disadvantage of course is that limitations are placed with respect to these data transfer. That is another thing that should influence our scheduling decisions, or in this case it is a binding decisions. All of these data transfers need to be made, and I need to bind each data transfer to one of these resources. These buses are the resources to which the binding needs to be made. So, this binding problem shows up in different forms in different stages of high level synthesis, but the one that we will focus on to illustrate it is the register allocation problem. In fact, variations of that could be used to handle other binding problems also. Registers in high level synthesis, the basic idea we had already seen. These are inferred from scheduling decisions that we have already made. The inference is that if you have data being transferred across clock cycles, then by default we infer a register which stores the data at the end of one clock cycle, and that data is available on that register to be used in a different clock cycle. Exceptions are there, but the general case is this: when an edge, graphically if an edge crosses one of those clock cycle boundaries, then there is the need for a register. Exceptions would be, let us say there are two adders here, right. One is this, so this pink adder is one and the yellow adder is different. These two operations are shared on the same adder. That adder does only one operation in this example. If that is the only thing that it is doing, and let us say C and D were held stable in the first clock cycle, and therefore I have a result. If they continue to be stable even in the second clock cycle, then that output's value is not changing, and therefore, since that is not changing, that could be used as input to the next operation. So, in such cases there is a possibility, but in the general case, when an edge crosses a clock cycle boundary, we infer a register. Problem of course is that for example, we want to minimize the number of registers here. So, a graph is scheduled in this way, and the objective is to minimize the number of registers, where so a register is inferred whenever any data edge or any dependence edge like that is crossing a clock cycle boundary. If an edge crosses multiple clock cycle boundaries, then what does it mean as far as the register inference is concerned?
It has to hold its value.
That register has to hold the value for multiple clock cycles, right. This problem is formulated by introducing what is called a lifetime of variables. Remember, variables are these, right. On the edges you have labels, those labels correspond to variables. Some of them may not appear explicitly in your program. In your code you might not have that variable, but nevertheless that dependency might still be there because of the result of the schedule. If you have a schedule like this, this could be the result of scheduling an expression a plus b plus c. So, that edge did not necessarily correspond to any variable that you declared in your code, but nevertheless it is inferred. You can assume that there is a temporary variable or something internally generated name of a variable that corresponds to that edge. So, some of them may be labeled by names that you chose, but there are other edges that did not necessarily have a name that corresponds to anything you wrote, but we will still call it a variable anyway for this purpose. Okay. So, I have a DFG that has been scheduled, and let us define lifetime of a variable in this way. That variable x, the lifetime for it begins after the first clock cycle, right. This is when the data is ready, that is when I will store the output x in a register, and I need the value of x, actually I need it here in that subtraction, and I also need it here for that addition. But after this clock cycle I do not need x anymore. So, I will say that the lifetime of x is this, starts with the first clock cycle where I need the value, that is what is called a definition, ends with the clock cycle beyond which I do not need the value. So, it is produced here, it is produced at the end of the first clock cycle. So, it is clock cycle 2 onwards when I need it. So, that is where it is defined. So, definition starts at 2. So, the lifetime starts at 2. The definition to the last use, the last use is in clock cycle 3. I do not need it beyond 3. So, that is the lifetime, starts at 2 and ends at 3 for variable x. Y is an input to this graph, perhaps it was produced by some other node before this flow graph. Fine, I am using y here, that is the first, that is the definition, right. So, I starts here, and among all the dependent operations of y, you see that this is the one that is scheduled latest. So, that is the lifetime for y. Okay. The one for z starts here. Similarly, I see that this operation will need it. So, that is the lifetime for z. So, similarly, I identify the lifetimes of all the variables. Why are we doing this? How does it help to identify the lifetimes?
Sir, after the lifetime we can free the register that was storing its value so that we can use it for that purposes.
Right, these variables are going to be stored somewhere, they are going to be stored in registers, and the information that is being captured locally here is the register that is storing x needs to store it only for clock cycles 2 to 3, beyond that it does not need. Since it does not need, that resources, the register resource could be reused to store something else.
This reduces our space complexity.
Reduces as?
Space complexity, I mean less number of registers.
Yeah, our objective, we have to define what is the objective function. Given the scheduled data flow graph, our objective function is to minimize the number of registers that store all the variables that need to be stored. Here too we could come up with several different strategies. Let me illustrate here a general strategy for solving the register allocation problem. Here is a way to represent this. Let me have a node corresponding to every lifetime interval that is identified. So, for every variable I have a node in the graph, and an edge between two nodes x and y is introduced in that graph if the lifetimes of x and y are overlapping. So, you see why it is called a conflict graph. What is the conflict if there is an overlap?
Simultaneous registers.
They can't be, since they both need to be alive, we need to maintain both of their values at the same time. At least one clock cycle, overlapping defined as there is at least one cycle in which we need both the pieces of data. It is a conflict as far as their possible mapping into registers is concerned, the same register cannot hold both the values. So, that is all. So, one node for every variable and an edge in the graph if the lifetimes are overlapping, which implies a conflict as far as our register allocation is concerned. Then this register allocation problem could be the side effect of solving one of the classical problems of graph theory, which is a graph coloring problem. Okay, if you color the conflict graph, we have to define what does the coloring mean. So, coloring problem is defined as assigning color values to each of the nodes in the graph in a way that if there is an edge between two nodes, then they do not get the same color. Okay. So, you can see that this example here, the way we have colored these, Z and R have the same color, Y and Q have the same color, X and P have the same color. This respects that constraint. Constraint is that if two nodes are connected by an edge, they cannot have the same color. So, objective of coloring the graph is you use the minimum number of colors, okay, to color a graph while respecting the constraint that connected nodes connected by an that are immediately connected by an edge, not that there is a path between them, but they are not connected by an edge. Then you, if the two nodes are not connected by an edge, you could assign the same color, but if they are connected by an edge, then you are not allowed to use the same color. Okay. That is the graph coloring problem. Chromatic number refers to the minimum number of colors that you need for coloring a graph. So, we can go ahead and color this. How does it help solve the register allocation problem?
Yes. So, number of colors will be the number of registers.
Number of colors would be the number of registers. Why?
If we add all the different colors, these are the minimum required in a given cycle.
Right. So, what does that color tell us? If two nodes have been assigned the same color, they did not have an edge, and therefore, they are candidates for sharing on a register. So, the number of colors we are using is an indication of the number of registers I need, and each color in fact translates to a sharing decision that we have made for variables on a register. So, that color tells me that I have decided to share X and P onto the same register. Okay. So, in a straightforward way, you can see that there is a mapping from a well known graph problem into the specific problem of register allocation that we had. Okay. This does not make it any easier, it is just pointing out that there is an association, there is a parallel between the problem that we are solving here and a well known problem. What that means is that solutions that are there to that well known problem could possibly be used by us, adopted in a straightforward way. Once we have composed this conflict graph, we could use one of these standard well known graph coloring algorithms and solve our register allocation problem. This kind of an analogy is very important. We do not want to reinvent the wheel where there are known good solutions. Of course, we would like to adopt the good solutions for our problem. So, then the problem just translates to the synthesis problem translates to the modeling of that problem in terms of one of the known problems, so that we can use the solution to that known problem. Okay. This is a known problem, but the what is not so great is that it is known to be a difficult problem. Right. So, we did identify something, but that does not take us any closer. Well, it does take us closer because it is a well studied problem. So, good solutions are there out there that we do not have to reinvent, but they too do not guarantee anything. But we are in comfortable zone right there, because all through in our discussion we have not been guaranteeing anything anyway, just pointing out that all of these problems are difficult, and what we are actually pointing out is something that is practical, but not necessarily making any theoretical guarantees. That does not mean that I stop as usual, since the problem is important, we still need solutions. You can see that it is not hard to come up with some solution for the graph coloring problem. Finding the optimal chromatic number may be difficult, but finding a solution that works can't be that hard, right. So, that growing cluster that I referred to could just be a simple heuristic, in which let us try to build that heuristic right now. You start with a random node, okay, and assign it some color, does not matter, it is the first node that is being colored. So, assign it red. Then my objective will be to find other nodes that can also be colored red. In a locally optimal way, I can just go ahead and find all the other nodes that could be given red color. Could that be a hard problem? It can't be. What is the algorithm? I just iterate through all the nodes, and if there is an edge with what is already colored red, I am not allowed, right. But if I find a node like R which is not connected to Z, then is it safe or to color it red, or should I look at it? Is safe. As of now, it is certainly safe. We are in the first iteration, right. After that, I still continue. So, let us say I found R, and then I still continue the iteration over all the nodes, right. I find a new node Q. What is my algorithm now? I should check whether Q has edges to any node that has been colored red. So, not just Z, but also R, because I have already taken the decision for R, right. So, at the end of one iteration, I have found all the nodes that should be colored red. It is at least a consistent solution. I did not guarantee anything through this process, but I am guaranteeing that I will find some solution. It might not be the minimum chromatic number that way, but after that I remove all those nodes from consideration that we have already colored. I am now left with a smaller graph on which I run the same algorithm. So, that is the growing clusters heuristic. It is a very simple one, but it could be part of a practical solution, of course. That is one thing. The other thing is that an efficient solution does exist for straight line code. Straight line just refers to code without branches, that is within a DFG. That is important here. What we scheduled here was a DFG, right. This was a DFG. There is no control here, there is no branch here. So, the point being that from the DFG I generate these lifetimes. There is the question of finding the optimal register allocation for those lifetimes. It is eminently possible. I did not talk about that algorithm, I just introduced the most general formalism. Of course, once you translate it that way into a graph coloring problem, graph coloring is indeed a difficult problem. But for this special case where you are only working within a DFG, this can be very easily solved and solved optimally. Where it does become difficult is extending the register allocation problem to work on a control data flow graph. Then you can see that so this is one DFG, but before that I had some other DFG, right. Now, these x's, y's and so on, at least the y's and z are also occurring in this DFG. So, the register allocation problem has to be solved globally for the entire CDFG. For example, that register that you chose for y has to be the same as the register that you chose for y in the other DFG. Now, this problem that we solved is a local problem within the DFG, but the register allocation is beyond that, because there are some variables, there are some variables like p that seem that they are local to that DFG, but there are others that are global. The k that is going out is going into some other DFG. So, you could solve it optimally locally, but then you end up with a problem if y is assigned to register R1 in one DFG, but as part of the register allocation solution to the other DFG you assign a different register for y. Right. Then that is where the suboptimality is introduced. Within a DFG you do not really need to formulate it as a graph coloring problem. There are other ways of solving the same problem. But of course, couple of reasons why we pointed out. One is that the general problem is indeed solved using a graph coloring. There are other equivalent ways of solving the that same problem without necessarily going into the graph coloring, but you can prove that it is an NP hard problem. That register allocation problem is a difficult problem. There is a different reason why you may want to go for that formalism, for the graph coloring formalism for register allocation. It is possible to incorporate some other factors as part of the problem formulation itself. For example, a measure of an interconnect cost could be annotated onto the edge weights. These edges that we had were simple edges, right? Either it was there or not there, depending on whether there was an overlap or no overlap. But that is just one variation of the problem. Even in register allocation, it could be that some solutions are better than the other because there is a downstream requirement on muxes and so on. Right, that we did not take care into account. So, there may be multiple register allocation solutions that have the same number of registers, but they are not necessarily the same area because later on extent of sharing is different, the implication on muxes is different. We will point that out later on, but as of now we did not take anything else into account. But if we wanted to, then the graph coloring formulation is good because we could annotate some interesting information onto those nodes, onto the edges in the graph. That was the discussion on the register allocation. We did say that the particular manifestation of the binding problem that we studied is register allocation, but this kind of a strategy of building a conflict graph and asking some questions on the conflict graph is a general mechanism for solving many different binding problems. Here it was variables being mapped onto registers, but there is this other problem of function units being mapped onto resources. That too we could solve using the same or a variation of the same strategy. In all cases, it could be that building a conflict graph and asking questions could be useful with respect to how resources will be shared for different elements, different nodes of the graph. So, the conflict graph is still there, but it means different things based on what problem you have actually captured in that conflict graph. We can take a look at a few topics that are tentatively considered advanced here. It is advanced only with respect to the basic algorithms that we looked at. It's in reality it is not so advanced, it is actually very necessary commercial tool that does high level synthesis most definitely needs to worry about such things. So, one advanced topic we already looked at, which is an extension of that resource constraint scheduling problem. In reality, it is likely to be an area constraint, if at all, not necessarily just the count of a resource being constrained. But a few other things we have alluded to as we had these discussions, we can point out in this section of the HLS discussion. Okay. So, first is IO scheduling modes. These are interesting variations that did not occur in the basic formalisms of the scheduling that we looked at, but there could be protocol related requirements of the particular design that you are making, which may insist that a particular behavior be maintained with respect to timing. It could be that cycle by cycle there is a specification of when what happens as far as the external inputs and outputs of a particular design are concerned. Internally it does not matter what you do because nobody is able to see it, but from outside there could be a requirement that says I give you this data at this clock cycle, you give me the result 2 cycles later and exactly 2 cycles later. This you can see is a variation of that deadline problem, time constraint scheduling problem, but in fact this could be extended to particular pair of nodes in the graph. It does not have to be for the entire computation. The variation that we looked at, the entire computation a deadline was set, but instead it could also be that I take a pair of nodes and impose a timing constraint on them. That is the class of this IO scheduling mode. It could be that the cycle by cycle IO behavior is fixed. Other computations that are internal, they are up to the scheduler, but the IO behavior cannot be changed. Specifically what it means is, if you fix that, then you are not allowed to add extra FSM states. Remember the flexibility that we started off with, which we said that the scheduler has, is that DFG is given to us and we take the decisions of when what will happen. But if I fix the schedule of some of the nodes, it means that I am giving up a part of that flexibility. Here these are IO nodes, which means that externally visible nodes, the schedule, relative schedule is fixed, but internal nodes you can still schedule them whatever. So, the scheduler still has work to do, even if it respects the cycle by cycle IO behavior. So, it is not allowed to add extra states, but in a state what happens, it may have some flexibility. On the externally visible nodes it has no flexibility, but for some of the other nodes it does have some flexibility. So, that is illustrated in an example here. The language used here is system C, but that is all right. This wait translates to our wait until clock event and clock equals 1, wait on an edge. So, there is in general the weights, like we said, they can be distributed anywhere in the code, of course, but these weights in general could mark cycle boundaries. So, that operations that you perform here, if they were IO, if P was an output and X was an input and Q was an output. So, all of these, if they were externally visible operations, then there are certain requirements that are fixed. What is that requirement? So, let us say that weight corresponds to a state, this other weight corresponds to another state here, and that third weight corresponds to, this is okay, right? This is how that that FSM would be inferred from the code that you have written. Normally we could expand the path from one weight to the other weight into multiple states if necessary, but if I am fixing the schedule, it means that you do not have a choice. If you do not have a choice, then it means that this test for X and the assignment to P, all of them has to happen in that transition from S1 to S2. Here we are annotating the actions onto the transitions in a melee format. So, IO operations that are there between two weights are constrained to be scheduled all into the same cycle. Okay. As long as there is a path from one weight to the other weight, all the IO operations there have to be scheduled into that one cycle. So, that there is a path from S1 to S3 directly, right, because in that other branch here you do not have a weight. So, P equals 2, Q equals 1 followed by R equals 1, all of them actually have to happen in the same cycle. That is the requirement of an exact IO scheduling. Non-IO operations can be scheduled anywhere if there are arithmetic and logical operations that others are not able to see, but IO operations need to be scheduled into specific cycle. So, from behavioral code like this, you see that you need to infer an FSM that looks like that, and sometimes that might actually show up as coding style restrictions that a tool might impose. So, maybe they will say that this is not allowed. But if you have a weight in one branch, then you must have a weight in a different branch. That restriction may be imposed. Is this acceptable? That depends on your design. If the protocol did not allow, then it is not acceptable. It is okay from an FSM generation point of view, you know exactly what to pick up and put where, but it is an unwanted addition of a state. If I insist that you must have a weight there, that translates to a new state that is there in the FSM. Now, whether it is okay or not okay, it depends on the situation. If this were to be strictly IO fixed scheduling, then that is an unwanted addition. So, it is expected that a tool be able to handle such situations and handle IO in a way that is correct with respect to the specification. Okay, let me stop here and we will continue with some of the timing approximations that we are making and what difference they would make to the synthesis strategy.